Proceed only after you read Chapter 13 and complete reading assignment 13 on Blackboard. In Chapter 10, we tested the equality of two means. In this chapter, we test the equality of three or more means simultaneously. We do this by exploiting the variation that exists between sample means. If the variation among sample means for the different populations is small, then the population means are probably the same. If the variation among sample means for the different populations is large, then the population means are probably different. Analysis of variance, denoted AN for analysis, O for of, VA for variance, and pronounced ANOVA, can be used to test for the equality of three or more population means. Data obtained from observational or experimental studies can be used for this analysis. In this chapter, we want to know if the means of several populations are equal using X bar 1 to estimate the mean from population 1, X bar 2 to estimate the mean from population 2, and X bar 3 to estimate the mean from population 3, etc. We use the sample means to test the following hypotheses. The null hypothesis: all population means are equal simultaneously. The alternative hypothesis is there is at least one population mean that is either larger or smaller than the others. If the null hypothesis is rejected, we cannot conclude that all population means are different. Rejecting the null hypothesis means that at least two population means have different values. For each population, the response variable is normally distributed. The variance of the response variable, denoted sigma square, is the same for all of the populations. We can test this assumption. In Chapter 11, we tested the equality of population variances. The observations must be independent. We can test this assumption. In Chapter 12, we tested for independence. If the null hypothesis, all population means are equal, is true, then mu1 will equal mu2, which will equal mu3. We can denote all of them as simply mu. If the ANOVA assumption that the populations all have the same variance, then the sampling distribution's variance is sigma square divided by sample size n. Hence, the standard deviation of the sampling distribution is sigma divided by the square root of the sample size. Thus, we expect samples from the populations to yield sample means that are close together, hovering near the population mean, mu. In the graphical example, X bar 1 is slightly above the population mean. X bar 2 is below the population mean. X bar 3 is above the population mean. If the sample variances are close together, the variance of the sample means is going to be small. If the null hypothesis, all population means are equal, is false, then population means mu1, mu2, and mu3 won't be equal. Notice that the ANOVA assumption that the populations all have the same variance is true in this graphical example, because the sampling distribution's variance is equal to sigma squared divided by n, or the sampling distribution's standard deviation is equal to sigma divided by the square root of n for all three populations. Thus, we expect samples from the populations to yield sample means that are not as close together when the null hypothesis is false. In the example, X bar 1 is located near the middle of the number line between the means of populations 1 and 3. X bar 2 is way above X bar 1 and greater than the mean of population 2. X bar 3 is well below both X bar 1 and X bar 2 and the mean of population 3. If the sample means are far apart, the variance of the sample means is going to be large. ANOVA tests for the equality of k population means. The closer the sample means are to one another, the more evidence we have in support of the null hypothesis that all population means are equal. That is, if the variance among the sample means is small, there is more evidence in support of the population means being equal. In ANOVA, we use and compare two estimates of population variance sigma square. The mean square due to treatments is equal to the between treatments estimate of population variance sigma square. The mean square due to error is equal to the within treatments estimate of population variance sigma square. When the null hypothesis is false, mean square due to treatments is going to be greater than mean square due to error, which is always a good estimate of population variance sigma square. When the null hypothesis is true, mean square due to treatments is approximately equal to mean square due to error, which is always, again, a good estimate of the population variance sigma square. Since there are k populations or k treatments, there are k population means to estimate. We estimate each of these with means of samples drawn from the k populations. For example, suppose there are 3 different formulations of gasoline, one that improves power and performance, one that contains a high concentration of ethanol, and one that is inexpensive. In this case, k is equal to 3. The variable of study is average fuel economy, denoted x. Hence, you could run the gasoline formulations in, say, 30 cars simultaneously in the same region of the country under the exact same conditions. The null hypothesis would be cars running on different gasoline formations had the same fuel economy. For the first population, j equals 1. Sample mean x bar 1 is computed from a sample of size n1. X bar 1 is used to estimate the population mean from population 1. For the second population, j equals 2. Sample mean x bar 2 is computed from a sample of size n2. X bar 2 is used to estimate the mean from population 2. For the third population, j equals 3. Sample mean x bar 3 is computed from a sample of size n3. X bar 3 is used to estimate the mean from population 3, etc. For the kth population, j equals k. Sample mean x bar k is computed from a sample of size nk. X bar k is used to estimate the mean from population k. The overall sample mean is denoted x bar bar, and is equal to the sum of the k sample means divided by k. The between treatment estimate of sigma square is called the mean square due to treatments and is denoted MSTR. Its numerator is called the sum of squares due to treatments, denoted SSTR. Its denominator is called the degrees of freedom associated with the sum of squares due to treatments. If the sample sizes are identical, intuitively, the mean square due to treatments is the product of n and the variance of the sample means. Since the variance of the sample means is sigma squared divided by n, the mean square due to treatments is an estimate of n times sigma square divided by n. Canceling the n's results in an estimate of sigma square, which is a good one under the null hypothesis. The within treatments estimate of population variance sigma square uses sample variances computed from samples drawn from the k populations or k treatments. For the first population, j equals 1. Sample variance S1 squared is computed from a sample of size n1. S1 squared is used to estimate the variance from population 1. For the second population, j equals 2. Sample variance S2 squared is computed from a sample of size n2. S2 squared is used to estimate the variance from population 2. For the third population, j equals 3. Sample variance S3 squared is computed from a sample of size n3. S3 squared is used to estimate the variance from population 3, etc., etc. For the kth population, j equals k. Sample variance sk squared is computed from a sample of size nk. Sk squared is used to estimate the variance from population k. The overall total number of observations in all samples is denoted nt and is equal to n1 plus n2 plus n3, etc., plus nk. The within treatment's estimate of sigma square is called the mean square due to error and is denoted MSE. Its numerator is called the sum of squares due to error, denoted SSE. Its denominator is called the degrees of freedom associated with the sum of squares due to error. Intuitively, the mean square due to error is a weighted average of sample variances. Hence, it is a good estimator of population variance sigma square if either the null hypothesis or the alternative hypothesis is true.